In the previous lecture, we learned that in order to make true statistical inferences, we need to learn a little bit about the theoretical world, about probability theory. So to get some of the basic ideas, let's again consider that case where I was flipping a coin that was either heads or tails, and let's suppose I'm going to flip it twice. So we do an experiment which involves flipping a coin twice each time we get heads or tails. Well, what can we say about an experiment like that? First of all, we can say that there are 4 possible outcomes to this experiment. Namely, we could have gotten heads and then heads, or heads and then tails, or tails and then heads, or tails and then tails. So we have 4 possible outcomes. Now in this case, because the coin is symmetric, it's equally likely to come up heads or tails each time, we can say that each of these 4 possibilities have equal probability, have probability 1/4. So we can say the probability of heads heads is 1/4, and the probability of heads tails is 1/4, and so on. So now we know the possible outcomes and the probabilities. Well, we can also start discussing various combined events. For example, suppose I say, well, to keep it simple, what's the probability that in this experiment I end up with a total of 2 heads? Well, that's easy. The probability of 2 heads, the only way I could have gotten that is if the outcome was heads heads. So the probability is the same as the outcome of heads heads, which we know is 1/4. Or you can also call it a 25%. What about the probability of getting exactly 1 head? Well, 1 head we could have gotten if the outcome was heads and then tails, or if the outcome was tails and then heads. So that probability is 1/4 plus 1/4, which equals 1/2 or 50%. Similarly, we can compute other probabilities. For example, the probability of getting some outcome, well, that's the probability of heads heads plus the probability of heads tails plus tails heads plus tails tails, which adds up to 1 or 100%, as of course it must, because we're always going to get some outcome. Or we can think about, for example, a random quantity. Like, for example, we can let y stand for the total number of heads. Then we know that, for example, the probability that y is 2 is the probability that we got 2 heads, which means we got heads heads, which has probability 1/4. And the probability that y equals 1 is the probability that we got either heads tails or tails heads. And that probability, as we know, is 1/4 plus 1/4, which is 1/2 or 50%. So we say, okay, in this way we can compute random quantities and their probabilities based on the different outcomes. So now let's try to make this a little bit more general by giving the basic rules of probability. So we can say that in any probability experiment, we have a collection of possible outcomes, which is normally written as a capital S, and it's called the sample space, and it's the set of all possible outcomes. For example, in the experiment I just described, it's the set of heads heads and heads tails and tails heads and tails tails. So that's the sample space. Then we can say that an event is any subset of S. So for example, it could be the event that we get exactly 1 head. That would be an event because it's a subset of all the possible outcomes. It's a subset of the sample space. Now we can say that any event A has a probability which is written P of A, and it's some number in between 0 and 1. Or you could say in between 0% and 100%. So that seems pretty clear. We could also say that if we look at the probability of the entire sample space, well, that should be the probability that some outcome occurs. And just like in the previous example, that should be 1 or 100%. There's another rule that we used before, which is sort of the complement event. That is, if we say the probability of A complement, which is to say that A does not occur, well, that's the opposite of A occurring. So the probability is 1 minus the probability of A. If we look at that in terms of the flipping 2 coins, we can say, for example, the probability of getting at least 1 head, well, we could compute it as the probability of heads heads or heads tails or tails heads, but we could also compute it as 1 minus the probability of 0 heads, because that's the opposite of getting at least 1 head. And then it should be 1 minus a quarter, which is again 3/4. So we have two different ways of computing the probability of getting at least 1 head using this general rule that the probability of A complement is 1 minus the probability of A. Now, you might be wondering, what does it even mean to say that we have a probability, like the probability of, heads, tails is equal to a quarter? Well, we'll pretty much stick to that as being a theoretical world statement. It's saying that we have a probability model, we have a theory which says that the probability of getting heads and then tails in this experiment is equal to a quarter. There are other possible interpretations that we should at least mention. One of them is the so-called long-run interpretation of probability, which says, well, if we repeated this experiment over and over again lots and lots of times, then the fraction of times that we got heads, tails should be close to a quarter. And that is true, as we'll see. So that's another way to think about probabilities. There's also the subjective interpretation of probabilities, which says, look, in my opinion, the probability of getting heads and then tails is a quarter, and that's just my opinion, and that's the subjective probability. For the rest of this course, we'll pretty much stick to the theoretical interpretation. We'll say we have a probability model which says the probability of heads and then tails in this experiment is a quarter. So now let's consider a second example, and for that example, let's remember the experiment in the last lecture where instead of flipping a coin, we flipped a bottle cap. And we said, well, we don't know what the probability is of this bottle cap coming up red or silver each time. But suppose we were to flip the bottle cap twice. And for now, let's just suppose that we knew that each time the probability of the bottle cap coming up red was equal to a third. Of course, we don't know that, so we'll come back to this. But let's pretend that we knew the probability of red was a third, and therefore the probability of silver was equal to 2/3. Then suppose we flip this bottle cap twice. Well, then we can again talk about the possible outcomes. So here we have a sample space consisting of, well, the outcomes red, red, or red, silver, or silver, red, or silver, silver. Now in this case, the probabilities are not all equal. In this case, the probability of red, red is equal to a third times a third, which is a ninth. And the probability of red, silver is equal to a third times 2/3, which is equal to 2/9. And the probability of silver and then red is equal to 2/3 times 1/3, which in this case is again equal to 2/9. And the probability of silver and then silver is equal to 2/3 multiplied by 2/3, which is equal to 4/9. So now we have some probabilities which aren't all equal, but we can still check that the probability of the whole sample space should be the sum of these 4 different probabilities, and sure enough, it still adds up to 1 as it has to. We can also compute other facts. For example, suppose we were to let x be the total number of reds that we get in the 2 flips of the bottle cap. Well, then we can say, for example, the probability that x equals 2 is equal to the probability of getting red, red, which is 1/3 times 1/3, or 1/9. And the probability that x equals 0, let's say, is the probability that we got silver and then silver, which is 2/3 times 2/3, or 4/9. The probability that x equals 1 is the probability that we got exactly 1 red in the 2 flips. Well, that's the probability of either red and then silver, or silver and then red. So that probability is equal to 2/9 plus 2/9, which is equal to 4/9. So in this way, we can compute all sorts of things about different probabilities of outcomes and events, and different quantities like x or the y we had before, which are sometimes called random variables because they're random quantities. We can compute the probabilities for them too. So in this way, with these very simple examples, we have just the basics of how to compute probabilities, some basic rules about sample space and outcome and probabilities and events and random variables. And now we're ready to start understanding some more concepts involving probabilities.